All right. How is it going, folks? Happy Sunday. I am just getting things set up here, so if we run into any technical difficulties, feel free to drop anything in the chat. Um, this is the first stream in almost exactly 365 days. So I definitely did not stick with this while I was changing jobs and doing some things like that. And got pretty busy. But for folks who are not familiar, a couple weeks ago, I guess about 2 months ago, I kind of put out this blog post. In fact, I'll go ahead and pull it up here. Let me also check my audio. Sounds like it's going through okay, but if you have any issues, feel free to let me know. I'm going to go ahead and jump off just looking at my face and jump over to the default stream here. All right, so what we're working on today and what we were working on in the streams I did a little bit back was the Moss Computer project. So basically, this is my goal or project to build a full stack computer, if you will. So the intention is for it to be vertically integrated. And so we're starting kind of down at the processor level and then building up and thinking about potentially building a compiler that targets it or using, existing compilers. We're going to be using RISC-V for this core, or at least for the base part of this core in this computer, and also building things and running things on top of it. So we're going to see where all it goes. The goal here, as I outlined in the blog post that I wrote, and I'll go ahead and just pull that up, is to basically learn more about chip design. It's something that I've always been deeply interested in, but haven't had kind of enough time to really invest in it. And it's not my background. So I think it takes me a little bit of extra investment on the side to be able to build up a skill set here. And so that's basically what I'm doing on these live streams. One of the things that's been frustrating for me is that I feel like for someone who doesn't have a background in this, my background's in computer science. Obviously, I'm aware of many of the concepts and interact with them through a number of layers of abstraction, but actually kind of like building up the skill set where either I'd go work in a position where I was, designing IP, which I'm not sure if that's necessarily what I want to do. But if I was to do that, if I was to want to do that, or just wanted to, design chips on my own, which, the barriers to entry are lowering. So basically, I feel like the resources aren't really there to be able to do that easily, or even potentially do that in a difficult manner. And so that's one of the reasons why I'm wanting to live stream a lot of this, just so the next folks that come along are able to not make many of the mistakes that I probably have or will make, and also potentially just interact with the community. I know on some of the streams I did last year, there was a number of instances where I learned from people in the chat or people who watched it back. So anyway, that's kind of the goal today. I am kind of getting back into the swing of tooling, concepts, etc. I literally have both my Patterson and Hennessy. Let's see if I can get it on there. The computer organization design book, as well as the computer architecture books behind me. So I'll be referencing them and trying to draw things up as it comes. But anyway, let's go ahead and jump into it. What we're doing today is kind of getting reacquainted with Vivado. So I'm starting off with, and maybe I'll switch the stream here again to be able to show it a little more closely. I'm using the RD A7 board here as the FPGA dev board. Has an RTX 7, which is made by Xilinx, which has been acquired by AMD. I'm using this as the basis for working on things at this moment. So let me switch back over. The kind of like IDE that is offered is called Vivado. You may have heard of Vivado because it has about 60 gig install size. They might have improved that a little bit. But I recently upgraded to v2023.1, and so I'm just walking through maybe some of the changes there, as well as just, like getting reacquainted with design flow, and how we get from our Verilog to actually having a bit stream and putting it on the device. Also, I see Tarun is in the chat. Thanks for stopping by. I hope you're doing well. Haven't chatted in a while, but I see you on Strava from time to time, so good to see you. All right, so Moss is that's not what I want. Moss is the name of the computer for Moss Computer Project, so we're going to be doing most of our work here. Just to give you a little bit of an idea of how things are organized here, we have our docs, which I kind of continue to build out, talking about development. We're actually going to be working on Vivado docs today. Just some learning. So these are just terms in computer architecture that might be useful to folks. RTL is our registered transfer level. And so this is where the source for our designs come from. Last year we worked on implementing our UART, which we might actually revisit today. Top is just kind of the top of the design, which will, or the entry point of the design, if you will, which we will definitely be talking about today with Vivado. And then the reg file, register file, and ALU, which this is very primitive right now, are both components in implementing the initial RV64I, which is the 64-bit integer instruction set for RISC-V. So that's what we are working on implementing. So there's a variety of components that are going with that. Our sim directory is for simulation. So we're using Verilator, which allows you to write simulation. That one's obviously not doing anything right now, but it allows you to write simulation in C++, and we have some makefile targets to be able to do some of that. All right. So let's go ahead and open up Vivado. You can install Vivado in a, geez, I'm going to keep hitting that, it seems like. You can install it in a variety of locations. I have a blog post from a while back. This is for obviously an older version of Vivado and an older version of Ubuntu as well. But this kind of walks through how you can install it. I have also, let's see what some of the things we have on this branch are right now. So this learn Verilog is what we're going to be talking about. And I see Eduardo in the chat. Why another RISC-V core? Because I want to learn how to implement one, or I am learning how to implement one. So I'd be implementing regardless of instruction set. One of the reasons why I've chosen starting with RV64i is because of the software support. So we should be able to run code on the core that we build faster. But totally, of course, right, if I was going for a quick commercial application, probably building my own core would not be the place to start. All right, so looking at the docs, learn dev is where we have the Vivado docs. So I upgraded yesterday to 2023.1 and started kind of taking some notes for other folks to be able to benefit from. And so we can start here with, that's going to open in Chrome by default, isn't it? All right, let's pop it open here. This is how you get started downloading. So AMD, right, like I said, Xilinx was bought by AMD. So there's this unified installer where you can kind of choose what you want to install here. And it will kind of like go through doing it. Depending on what OS you're on, there's a variety of different steps. Yeah, we're not going to go through all of this today. It does take a while, and it's very large to install. I have installed it in, let's see, my home Xilinx directory. So you can see some of the components here in Vivado. We are going to have all of our supporting files, and then in this bin directory is where kind of all the executables are. And this Vivado executable is actually just a script that calls some other ones. But to get this going, we can go ahead and open Vivado with the GUI. And you don't have to use a GUI, but if we want to, we can open it like this. So here we see we're booting it up. Also, maybe just a note on my stream for folks who are interested. I'm actually using a different laptop for streaming and a laptop for actually doing the development work, which is nice because the workloads don't conflict. And I have a capture card going from my development laptop to my streaming laptop, and then my audio interface is plugged directly into my streaming laptop. All right, so we can see recent projects here. If we wanted to look in our directories here, if we go into toolchain and look at boards, we have the project file here, which this is specifying the attributes of our project, which allows us to reopen it in Vivado. So that is great. A bunch of these files I'm not committing to source, but the one that we are is our constraints file. So this is basically defining some components on the board that we're going to be using, as well as a bunch that we're not. And as you can see, this came from the Digilant repository. Eduardo with some more comments here. You can use OpenXC7. Yep, there is a lot of work being done on open source FPGA design flow. One of the reasons why I am not using those here is because I want to learn about some of the tooling that's used in the industry. But I certainly endorse using the open source design flow. And actually what I'm hoping is that after using some of the industry tooling, that I can move over to those and kind of like have a good idea for what the shortcomings are, as well as what some of the benefits are. Obviously, open source is a huge benefit. Massive shout out to people who are doing work there. Also hope to maybe contribute with some more experience as well. So thanks for pointing that out, Eduardo. Looks like Daniel's also here. Good to see you, Daniel. Daniel also does some great streams. So check those out. And yeah, Eduardo points out the open source stuff for various companies and boards and stuff is at differing levels of maturity. Unfortunately, the bitstream format for Xilinx is not super accessible, so folks are doing the hard work to be able to document that in an open source fashion. All right, so we mentioned the project file and the design constraints file. I have Vivado open here. I'm going to go ahead and open the project. All right, we're going to see the constraints here. And first thing we're going to notice is we have 3 of our Verilog sources here. And if we open them, we can see them in the kind of built-in editor here. So top is not including our, let's go out here again, is not including the components for our actual core here. Also heart and decode are not, they're just on this local branch right now. So top is just our UART transmitter and receiver. So we're going to see those files present beneath it. So from your design sources, if you want to add a new file to be considered, you can do that by just clicking plus there, or you can right click and do add sources, add or create design sources, and then you can just go in and select what you'd like there. You can obviously do some editing right here in Vivado. I don't love the tooling that's offered. I don't love the tooling that's offered. So what I typically do is use Vim or NeoVim in this case to do my editing. So let's say I just want to go in here and say, hello, whatever. Then we'll see that actually gets reflected here, and we can say reload, and it comes through. It's not great, and we'll talk about maybe some of the better options for editing flow here. All right, so there's a few steps, and I'm sure a lot of folks who already work with FPGAs are familiar with this, but we're starting out with this HDL. So I don't know if I actually have that in the terms over here, but maybe we'll start with or RTL, we could say. So RTL, so this is design source files written in a hardware description language. Whoop. Or they could be written in something like C, for example, because there is some high-level synthesis support in Vivado these days as well. We'll take a look at that in a minute. But basically, we have the steps kind of like organized in the order that you would run them. So simulation, you can see here, I have run synthesis once. That's why it's giving this an option. But if we just loaded this up and hadn't synthesized the design, then we would just have behavioral simulation. So that's where it's just evaluating the RTL. And then synthesis basically turns us into actual circuits, if you will. So actually, let's go ahead and just run synthesis here. And you can see there's a variety of options. You can actually even run it on remote hosts, but we'll just run it. When you start running synthesis, you're going to see it loading up here in the top right. And when it's done, it should actually grab control of the screen here and give us an update that it's done. It does take a bit. All right, so instead of running implementation, which is the next step, so if we look over here, simulation, we were just talking about that. We're going to dive a little bit deeper into this. RTL analysis is like the linting and that sort of thing. And synthesis is what we just ran. And we're going to look at the Vivado docs for that. So after we run synthesis, we haven't actually mapped this to components that are available on the FPGA, or something you'd be doing if you're like designing an ASIC would be like if you had a PDK, so a process design kit, then it would outline kind of the components that were available for including in your design, and so you could map basically your circuits to those. We're going to talk a little bit more about that as well. Let's see how many times I can say we're going to talk more about that. So we'll open the synthesized design. We might see a failure here. Yeah, so okay. So this is not actually mapped onto here quite yet. We can see the nets, but what I like to do at synthesis step is open the schematic. So this is actually looking at what our RTL got translated into. All right, so we will go. Let's look at the UART TX here. So you can expand and get a very deep view of what's going on here. Let's see. So let me pull up this UART TX. We can look at what's going on. Eduardo mentions that the open source tooling runs synthesis. Well, actually, it looks like runs implementation perhaps much faster. I also saw that quote somewhere. Was that on Twitter recently? So that's another reason you might want to try that out. So this is the UART transmitter. So if we look up at the module, you'll see that we have the clock and send signal, which the clock is just the system clock, and then send is basically just a 1 or 0 where we're indicating whether to send or not. I think that I had that mapped to a switch on the board, maybe. Let's see. Actually, it looks like I don't have it mapped to anything right now. But so that's basically say send or don't send, and then the clock is used. We can talk about how UART works in a bit, or watch one of the previous streams where we went through implementing this. But that's the input and output. This is the data we're sending, the 8 bits. And let's see, where are we looking here? So we can see some of those coming in and the outputs as well. So if we expand this, we obviously have a description of the behavior here in our setup here. So we're saying on every clock cycle, run this state machine, and based on the previous state, as well as some other variables, determine what to do here. So we might be advancing the state. We might be sending some data or something like that, or advancing through sending various bits of the data. Also, it looks like Jonathan jumped in. Good to see you, Jonathan. All right, so if we zoomed in here, we can see things that are actual components that we have available on the board. So I think I had this mentioned here somewhere. Let's see here. Just gonna grab that. And we'll yank that to my copy buffer. Pull that over. And we can see all of the design elements that are available here. So the one that we're looking at here is a LUT4. So if we click on that, you can get some more information about the properties here. So we can see it's a LUT or a lookup table. The reference name is LUT4. Number of cell pins 5, number of nets 5. Okay. So if we wanted to jump in and see what this looks like, we can get a description here in the docs. So 4-bit lookup table with general output. So the design element is a 4-bit lookup table, general output, and a init attribute with an appropriate number of hexadecimal digits for the number of inputs must be attached to the LUT to specify its function. So we are, this basically allows us to, implement some arbitrary logic here. Let's actually see if we have anything else over here. Clock count reg. Actually, the bit index one might be useful to us. That's a LUT3. Actually, let's look at the difference between, well, actually, you can see LUT3, 3 inputs, 1 output, LUT1, 1 input, 1 output, etc. So anyway, we can go through and kind of get descriptions of how these work. Oops. And you can see the logic table here. So, right, we have these inputs. We have the outputs that are based on the init. So it basically allows us to say, whatever logic we want to implement, since it's an FPGA, this allows us to dynamically do that or put in the bit stream. I don't know if it tells us anything about the init in here. I don't think it does. But it shows us that we're basically using a lookup table to implement it. And let's see if there's anything else. FDRE, let's take a look at what that is. Okay, so it's a flip-flop. clock enable, and synchronous reset. So this is what allows us to store a value and then update it based on a clock signal here. Also, you can see that if we wanted to actually instantiate one of these directly, we could do so. Cool. All right. Okay, so after synthesis, we can run implementation, which is going to take this net list and is going to actually map it to these elements on the device, right? So we're saying in this case, we need to use a lookup table with 3 inputs and 1 output, but we need to decide which lookup table element on the Arctic 7 FPGA that we have. Like, where is it going to be placed literally on the board? All right, synthesis out of date. That's kind of surprising since we just ran it, but we'll rerun again. Another thing to note here, which I want to look at more, is you can also orchestrate all of this via TCL commands or tickle commands. That TCL is tool control language that basically allow you to do this without a GUI. I'd really like to update the tooling to be able to do that so that we don't have to have this all open all the time. And you could just do this all from the command line and treat it more like a compiler, which would be nice. But let's actually look more closely at, let's see, open implemented design. Yes. All right, so here we can see some of the actual mapping of those elements onto the board here. Before we do that, though, I want to look back at the docs here. And I believe in one of these, it is going to tell us a little bit about these different steps. RTL analysis. Working with source files. I know in one of these, it goes through kind of the steps of, okay, here we're looking at a little bit. So design creation with RTL. And this is using this ultra fast methodology. So maybe we'll talk about that. Basically, it's like a best practices doc from AMD to help understand how to lay out your projects and how to be effective at using the tooling. I think there's some documents here. So we can kind of see the steps here that map. So logic simulation, logic and physical constraint assignment, logic synthesis, implementation, timing closure, and design analysis. So what I want to do is actually kind of like provide some better definitions here of each of these stage. Let's just actually Vivado steps. This might be the one we already have open here. Okay, wait, this is actually a little closer, I think. This is with a previous version, but this still is useful. Cool. Okay, yeah. So you can run a simulation after various steps, and basically you have more information at each. Yeah. So basically, running simulation early is effective for catching things earlier. Functional or register transfer. Does it behavioral? It's kind of annoying that it. I guess RTL simulation. Is really behavioral. So this is the earliest simulation that can be performed. So this is before mapping it to the actual elements. Let's say useful for identifying syntax issues and useful for identifying syntax issues as well as any mistakes in logic. And then after synthesis, we have some more information. So let's look at running logic synthesis. Actually, let's just keep reading through this. Also, interestingly, it says do not instantiate specific components unless necessary. So that's kind of, I believe, at least leaning towards the idea that try not to consider necessarily. Well, you obviously need to consider the resources that are available on a given board, but try not to be tied to them. And that way, yeah, it's more readable, right? Because you're not saying use whatever specific lookup table or something like that on this board. You're saying I want this behavior, and it should be able to get mapped by the tooling to the specific elements. However, actually, somewhat interesting, I feel like I wrote this blog post a bit ago. About the register file, and a bunch of the feedback I got about it was basically like, you haven't considered how this actually gets synthesized, and that's true. It wasn't the intention of the blog post, but I think the takeaway from that is to say that not that you shouldn't. Not that you should always consider exactly all of the elements that are available when you're writing the logic, but you need to consider after synthesizing the logic, hey, how does this actually get manifested? Because you may be using elements super inefficiently, right? Or it might be different for the target that you're targeting. Okay, so logic simulation, and like I said, also we're using Verilator kind of for this step right now. Compiling simulation libraries. Okay, so using a resolution of 1 picosecond. after synthesis or implementation. Okay. Post-synthesis functional simulation. I wonder if it actually... What I'm interested is post-synthesis timing simulation. It's actually pretty good stuff on the forum here that can be useful. Let's check here. Do we have 2023.1? Here we go. This is what I want. Okay, yeah. And another thing that I wanted to note down here is allows for simulating individual components of the design. So that's nice that we don't have to, do the whole system. So cool. And let's put this link in here. Offered in Vivado. See the documentation here. All right. Post-synthesis functional simulation. Oh, man. Got to retrain that muscle memory. Okay, post-synthesis. You can simulate a synthesized netlist to verify that the synthesized design meets the functional requirements and behaves as expected. Although it's not typical, you can perform timing simulation with estimated timing numbers at the simulation point. Okay, so that's helpful to know. That the timing simulation is maybe not the most helpful after simulation. I guess it does give you the ability to say, actually evaluate the components that are in use, but it doesn't. Since you don't have routing information, so you don't know like where on the board things are laid out, then you're not going to get super accurate timing simulation. I'm going to note that down. Timing constraints. It just says timing numbers. Simulation should also be performed following implementation. One of the things that I wanted to take a look at here is in the what some of the stuff Eduardo was mentioning earlier around open FPGA toolchains and that sort of thing. I have found this to be a pretty helpful, actually all of these, to be really helpful for understanding what's going on. Translating a hardware description language into a bit stream that can be programmed on an FPGA requires a number of steps. The sequence of these steps is referred to as the design workflow. A high-level view of, a generic high-level view of FPGA design workflows can be found here. So this is not specific to Vivado, but I think it's really useful and obviously maps to it. And actually, Vivado is right here. So okay, yeah, so we're talking about synthesis here. And where were we looking at? Here we go. Let's actually get a little more crisp about the definition between I feel like the HDL and RTL are kind of conflated here, but maybe that's okay. Synthesis is the process of translating RTL into a netlist. let's see if we have FPGA netlist. Place in route. Yeah. Okay. So it's a netlist both before and after. Um, the netlist describes the design elements that are used to implement the logic described in the HDL at this stage. At this stage, the netlist does not describe the exact elements, the design elements that are used to implement the logic describing the HDL. At this stage, the netlist does not describe which specific elements are used on the FPGA and how they are connected to one another. Physical elements, I'll copy that from the section below. All right, I'm going to get back to post-synthesis functional simulation. There's not a lot of info there. It's probably going to take me to the exact same place, yeah. Timing. Yeah, okay. So we're basically at this stage saying, what are the design elements that were chosen to implement the logic that we described in the HDL? Are they present in? Are they implementing the logic correctly? Right? Like, we're validating that the synthesized design matches the logic that we specified in our HDL. All right. I'm not sure that this is actually totally accurate here about the process design kit. I'm going to remove that for now, mostly because I don't know enough about that. Implementation is also known as place and route PNR. So basically, that's why we're able to then look at our board here, which or our FPGA here, which is the Arctics that I have on this board, and we're able to actually see where those elements were placed. So if we go in here, we can actually get an idea of the exact elements that are being used. So the same components that we saw in the schematic. Let's see if I can still open it. Okay, cool. Yeah, I can get both of them. So if we look in the UART-TX here, we saw we were using the D-type flip-flops. We were using the LUTs and that sort of thing. And we can also see, oops. Oh, man, it reverts it back. That's annoying. Open, implemented design. You can look at the schematic here too. Can I get the device again? Okay, yeah. Okay, I've got it. Sorry. So, right, like I said, when we zoom in here, we can see mappings to some of those other ones. So, B5 LUT. So that's a specific lookup table in this slice here, which we should probably talk about slices and CLBs, configurable logic blocks, at some point as well. Okay, but I'm going to skip past that for a minute, and let's actually do the last step here of programming. So I'm going to plug in my board. All right, so it's now lit up. Bitstream translation. See if there's anything on the Vivado docs. All right. Let's go ahead and generate the bit stream. Last step is going to be programming. Once the bit stream is generated, let's open Hardware Manager. Open target. All right, so it automatically discovered it. All right. And so we can either write it, I believe, to an onboard flash here, or program the Arctic 7 directly. Flash memory or directly to the FPGA. Either to flash memory or directly to the FPGA. All right, cool. Let's finish these out. On the accurate implementation of the specified logic. JTAG interface. Programmed. There are no debug cores. There are. Let's learn a little bit about debug cores. Here we go. This is pretty cool. Looks like you can just insert these into a design. All right. Dynamic function exchange. This is pretty interesting. So really what I was looking for was just bit versus bin, but it looks like that this is a lot more information about how you can dynamically load new configuration onto an FPGA. Um, so actually, probably not worth mentioning this here. I think it is interesting, but let's see if we can find something that just says Vivado bit versus bin file. Here we go. I know I've looked this up many times before in the past. Oh, interesting. So basically, this person's saying um, the bit file includes a header that has more information um, that allows for looking at, or it allows for doing JTAG configuration. Looks like there's actually a picture here. So there's the bin file. Yeah, okay. So I think that it mentioned there that the bitstream file, um, let's actually just note this down. Bitstreams can be generated as .bin or .bit files, with the latter including an ASCII header with information about the bitstream. All right. Bitstream file. Forget where it writes these. Hardware. Nope. Runs. Okay, yeah. Top bin. Just checking what's in all these. Okay. We don't care about that. Nothing in synthesis. Oh no. Hold on. Let me see if it's gonna. Cool. Okay. Vivado boards. Hardware. that. Oh, no. Runs and pull. There we go. This is what I want. And I want to shorten that. All right, let's use bit. Program. Let's make sure it works. And yep, we can see there that we programmed the hardware device. That seems good. Program with the design. Yeah, okay. And then we refresh the device. So these are the tickle commands that were used. I also have a note here about how we can connect. So TTY USB 1 minicom 9600. And then I think there's a reset on here. Let's see if that gives us anything. Doesn't look like it. I think that is because this design doesn't actually work. So last time I was doing this, I was trying to basically have it echo anything that that we could send data over UART and just have it echo it back to us. Let me try. Let's try and go out here. And we've got these LEDs down here on the bottom. None of them are lit up right now. So I'm just going to go through actually updating to set one of those. Although I think it might get overwritten with the LED assign LED 0 equals 1. And I know this doesn't make any sense, but I'm just gonna set that there so we don't touch it. Reload, run implementation, and it'll automatically rerun the synthesis for us as well. Oh, implementation failed. It doesn't like that. Actually, let's just do this for now. It might get mad about those not being used, but we'll see. don't think these are actual errors down here, so it's not going to worry about them. Let's just give it a try. I was actually thinking about for the linter, setting up NeoVim so that on save it would execute the Vivado linter. I don't actually know what the Vivado linter is called. Oops. Nice. Okay, so that worked. Generate bitstream. Xilinx. Vivado. Ben. It might not have a. It might not be a standalone. Okay. So generated, and then we want to program the device. Sure. All right, cool. And as we can see, the light is now lit up, so that's good to see. Maybe we could jump into actually fixing some of this now. So we've gotten a little bit of a Vivado introduction here. Let's actually see why this may not be working. So I know before that my actually, let's wrap up some of these, just make sure we have everything populated here. Get a general description of Vivado. I don't know if they call it a. It's now Vivado ML apparently. Missing a. Oh, that's strange. The T is different color. What do we call this? Design tool. We'll call it an ID. Development environment. Holy, I am really having the typos day. Interactive development environment. Developed. Let's see. Released by Xilinx. Now AMD. It supports wide variety of. Is it just for FPGAs? Is my question. That high level synthesis HLS. is what I was talking about writing logic in C++. Used to implement $1,000 man years and cost $200 million. Wow. Wide variety of tools used to implement logic design. So I think that one of the things that's still like a bit opaque to me is the difference between tools like this and like cadence and synopsis and those sorts of things. Actually, let's just Google it. Let's see. Vivado versus synopsis. How do you spell that? Here we go. Yeah, mentor graphics, synopsis, and cadence, I think, are the top three. That's not really helpful. Be used for IC design. Or is it just for FPGAs? System to IC level. This is interesting. Standard cell. Interesting. All right, so I think we're at a decent place with that right now. So looking at top again, we basically are using the UART pins here to be able to communicate. There is an FTDI chip on this board, which is a USB to UART, which is how we're able to talk over USB to the host here, which is my laptop. And like I said before, we were previously able to send when I essentially hard coded the what we wanted to send. So we could probably actually try that if we wanted to. Let's see, the send. So yeah, send was being driven by was previously being driven by a switch, and so I would flip the switch and it would send like hello, or something like that. We could try that here. Let's just say we're going to assign send equals 1 and assign data equals let's get our ASCII codes up here. characters. Let's say 1. We send a bunch of 1s. So I believe it's 8B would be correct. Okay, so we'll get that open again, and then let's try and run implementation, which should restart synthesis. So it looks like we had maybe a few other folks jump on. If you just jumped on, feel free to introduce yourself or join the chat. Running route design. Okay, let's just go ahead and generate bitstream. I feel like this might be a good time for a weekly stream, just given that I feel like a number of folks who I have interacted with in this space are in European time zones. All right, let's program the device. See if we. All right, so we are getting something here. Interesting. Okay, yeah, it's right. It's just not writing a new line, I think. Why is it not displaying correctly though? Feel like we hit this before in the past. Yeah, this is when we were sending this data, which was working fine. Yeah, I'm not sure why it's not sending that correctly. URTX starting with bit index 7. That all sounds right. So it is sending, so that's good. Also, we have LED 1 lit up, so it's also notifying. So that's good. I am going to see if I can map this to a switch here. Clock, LEDs, switches. Let's get rid of send, input, zero, switch. Oh wait, sorry. It can just be a, I think it can just be a wire. Let's try that and see. Okay, those are fine. I'm going to look up Minicom send UART. Generate bitstream. Okay. Ooh. Set property expects at least one. Maybe I do have to specify 0. I feel like that should be a 1, but given our other syntax here, maybe not. Set property maybe I still need to say 3, 0. And then just address which one, maybe? I shouldn't need to based on, I shouldn't need to based on the LED there. Let's just, for the moment, just do the same thing. Run implement, well, hold on. We'll just run the linter first. All right, that seems like it felt okay about it. Rating bit stream. Program device. All right, so it looks good so far because the LED is not lit up yet. We should also be, oh, we got something there. Let's see. Okay, yeah, turning the switch on calls us to start printing, and then we can see that our LED is lit up, and then this should stop. Yeah, and turn the LED off. Cool. All right, so that looks right. Cool. So getting back to where we were, though, we shouldn't need those. And I'm going to undo all of this. And then what I want to do is say when we receive data, then we want to light up LED 0, right? And we want to drive the data going the other direction. So the input, yeah. And then send is, so data is getting written to on each. We're updating data regularly, but then once we say send, so we assert the send, and then let's go back to idle. Okay, so I think that actually the issue maybe is that we're not giving, so we assert send and then we immediately go to idle and then deassert send. And so that says to me that we're probably not giving it an opportunity to write back. What I'm curious is if we just trying to think how we want to do this. We could just say, I want to test out that we're actually receiving. Maybe the we'll just set these to themselves. So while we're sitting in idle, then we don't change them. All right, so yeah, let's see how that works if maybe we just send one character and it reads it off. Let's give that a try. We really need to, like, what would be good is if we wrote it to a buffer and then, you know, I flipped a switch or something like that, and that would be, that would start indicating that it should start sending. Actually, well, let's try this. And then I want to see if we expand the data buffer and we basically read into it. We're always reading from the UART. And then once I flip the switch, whatever's in the data buffer, we'll start sending that as well. While this is running, we can take a look at the latest work that I'm doing. So looking at the instruction decode here. So this is the control unit for the RISC-V processor. So you can see these are the opcodes, or 5 bits of the opcode. Actually, let me go ahead and try. We'll do this for a sec. And after I switch that, I got a, would you like to take a 2-minute survey? No, I wouldn't. I am going to pull up the RISC-V spec. Okay, cool. I already have it open here. Let me switch this back over. Okay, so here we can see the opcodes. All of the opcodes, this is actually for 32G, which is IMFAD, ZI CSR, and ZI Fence I. We're just doing RV64I. So this is actually more than we need. But you can see here that for all of the opcodes, the lowest two bits are always 1 1. So this is 32i, and this is the ones at 64i, the instructions that 64i adds. And so basically what we're doing is decoding these opcodes, and based on that, the first thing I want to do is determine whether we are going to write the register. And so all of the instructions here that use a destination register are ones in which we want to write. We want to enable reg write, which is this signal that comes out. So for example here, write control actually is what we'd be specifying based on the opcode of the instruction. So basically after we, let's say it's an add instruction, for example, we'll get our two source registers, and then those will go to the ALU where the add operation will be performed. And then if the opcode specifies a destination register, we'll be using RD to write the result of that add operation back in. So basically reg write, which we can see here, is going to be driving write control on the register file. So this is done. We'll program the device. Okay, so interestingly, one of the LEDs already came on, LED 4 here. And so that one is being driven by the UART receiving. So send is not enabled, but it appears notification is. All right, let's look more into that. Minicom hardware control flow. Serial port setup. What is, oh, no. Oh, I see. We want to do no. Hardware flow control minicom. All right. So that was interesting. Let me see if I can reset this. I think that actually cleared it. Let's program it again. Okay, so I have the LED lit up again. And then I jumped over and I just typed hello. And if I hit enter, oh, okay, so it didn't work that time. Well, it seemed to work last time. Let's try that again. I am going, might be messed up. Oh, actually just closing and opening Minicom appears to do it. I'm going to program it one more time. Okay, yeah. So one is lit up and interesting. So I'm not getting anything from it when I'm not able to send anything to it. But opening Minicom does. Here, I guess I can show it lighting up again. Oh, just even leaving Minicom sends. And something is being sent here. It's probably just maybe a new line. So anyway, there's some more experimentation to do there. But I'm going to keep working with that. But I think for today, I'm going to go ahead and wrap it up. It's about 2 hours, I think, in. So pretty good stream here. Excited to keep doing these. Yeah, thanks, folks, for stopping by. If there's anything I could be doing to make these more helpful or interactive, obviously, I'm early still in learning about these types of things, but hopefully there's some useful information that comes of it, and we can keep experimenting and keep learning. But yeah, feel free to send feedback, and I'm always open to chatting. Hope everyone has a good end of your weekend.